So today's topic is predicates and atomic swaps. So how to add predicates to the Unicity and how to implement atomic swaps with predicates. You can turn on the next slide, please. We start from some basic cryptography, then recall how the Unicity works, and then say what the predicates are and how to implement atomic swaps. So let's start with the crypto basics first. So we have to go through signature schemes. First, signature scheme has 3 algorithms: key generation, generates public key and private key, and then it also enables to sign messages. M is typically a message hash, and it outputs a signature of the message. It uses the private key. And then we have verification algorithm that has public key as a parameter, as M and sigma as input, and it outputs 1 if the signature is correct. And verification identity says that if you generate keys properly, if you sign properly, then you will verify properly. And from security point of view, we require that it's hard to create signatures without having the private key, even if you can call the signing oracle. But the point is that you can't call the same M that you will, as adversary, output as a forgery. So this is called existential unforgeability under adaptive chosen message attack. Okay, let's now talk about commitment scheme. Commitment scheme, it's a simplified view, but it's a pair of algorithms: commitment algorithm and open algorithm. Commitment computes, given a message, computes a commitment of the message and decommitment of the message. Decommitment is usually secret. Commitment is published somewhere, and we have opening algorithm. So if we are given the secret, the decommitment, then we can open the commitment and reconstruct the message. And opening identity says that if you commit properly, you will open properly. Sometimes we only need the C, we don't care about the decommitment, and then we use a notation comC that just outputs the commitment. Okay, so from the security point of view, we have 2 security requirements. So first is binding. Once you have a commitment stored somewhere, you can't open it in 2 different ways. So the commitment really commits to a particular message. And hiding C, if you see only C, should not reveal useful information about M. Some commitment schemes are perfectly hiding. This means that C doesn't contain any information about M if you don't have the decommitment. There is also a very useful commitment scheme which just stores the message itself. This is called trivial commitment scheme. It's just basically you don't use commitments. So sometimes if you have an option, you have a generic commitment scheme in your construction, and then if you replace it with a trivial scheme, then this means that you don't use commitment scheme at all. Okay, let's now talk about predicates a bit. You can put on the next slides. Let's talk about the Unicity first. So the Unicity message flow. We have tokens. Say we have a token. Token has a state. State has 2 components: the owner's public key and a hash value. Hash value reflects somehow all the previous transactions with the token. And transactions change the ownership of tokens. The transaction is in the form, if you want to transfer a token from state S to another state, then you have to put the same age here as in the state. Then we have some data in the transaction, and data consists of the public key of the next owner, a random mask, which is just random L-bit number, and some other information that might be needed. It's called auxiliary information. We have to sign the transactions if we want anything to happen in the system, and the signature of the transaction is should satisfy the verification identity, of course. The M is computed, the message hash is computed as the hash of this hash, and the commitment of the hash of the data. Usually we, at least how it's now implemented, we don't use the commitment at all, which means we can replace it with a trivial commitment scheme here. So actually, V is just the hash of the contents of the message, data of the message. Now this is not all we have to do for a transfer. We have to certify the transaction by registering it in the Unicity service, or in the which is implemented as a sparse Merkle tree. And so we create a request which contains the public key, the hash of the state here, and the hash V, and the signature which we created for the transaction. And we send it to the service, and we get back an inclusion proof. And finally, we construct a certified transaction, which consists of the transaction itself, the signature, and the inclusion proof. And this triple is then added to the token ledger, where we have all the previous certified transactions with the token, and token is now in a new state, which is S prime, which has now the new owner, which was in the transaction, and we have a new hash here, which is just hash of the previous hash, hashed together with a secret mask here, a random mask. So this is basically how the state of the token changes when we execute transactions in the Unicity system. Let's talk about a bit about this Unicity service itself. So it just maintains a key value store. We denote it by R, and initially it's totally empty. Nothing is stored at any key, and the only way how something changes in this R is that the service receives the requests, and so the service serves requests that change R, and it also serves status queries, which just say what is stored under the key and do nothing else. They don't change R itself. So if a request comes, then we compute the key as a hash of the state of the token. So remember that public key and H form the state. And then we compute the hash M, which is the hash of H and V. And we check whether the place at this key is empty. If it is, and the signature verifies, then we store something under the key. And what we store is this value V and the signature. Then we create the inclusion proof and return it to the requester. Okay, and for status queries, we just need to know what is the key we want to know the information about. Either it's empty or contains something, and this is stored together with the proof to the user. This is sent together with the proof to the user. And sometimes we don't care about the stored signatures. We only care about this value, and then we just write the shorthand RK equals V. And we have a verification function. If we have a key and a value that is stored under the key, then we have inclusion proof, then we have a verification function that returns 1 if indeed it was so in the registry at the moment of obtaining this inclusion proof from the service. Okay, so this is how it's a simplified form how Unicity system works. Okay, let's talk about predicates now. So in mathematics, predicate is any function that has a domain and it returns either 0 or 1 for any argument of the domain. Sometimes we need to parameterize certificates. So we have families of same type of certificates that only differs with from a parameter set. And so for every fixed parameter, we have a predicate with certain domain. Okay. For example, if you have a digital signature scheme, we can construct a predicate from it. So the predicate is just it has a parameter, the public key, and it just given M and sigma, it just verifies M and sigma with a public key. Okay, so this is just one example how to create certificates based on cryptographic functions. Let's go on now. So how should we implement predicates in Unicity? So every predicate should have a name. We use this kind of notation, new name and parameters and some arguments that are missing right now. It's denoted just by a dot. So this is the write-up of a predicate. And these parameters, how many of them there are, what type there are of, it depends on the predicate's name. Okay, and the domain in Unicity predicates has two parts. So first, it has a standard part, which has two arguments. One is time, and the other one is a hash value, which are always there. And then we have a user or name-specific part, which depends on which predicate we are dealing with. So arguments are in the form. They are triples, which consist of time, a hash M, and an unlocking argument, so to say. So we have to add the concept of system time in the Unicity system. And this is defined by the Unicity service. When Unicity service got the new certificate from the BFT layer, then this integer is just incremented. New time has come. And also, we assume that when you have an inclusion proof, the system time can be extracted from the proof. So this, what you extract is the time, say, to a prime. It's the time when the certificate was, inclusion proof was created. Okay? Let's go on. Okay, examples. How to implement simple signature predicate, or in Bitcoin terms, paid to the public key predicate. We have one parameter, which is public key. We have standard arguments, which is system time and message hash. And we have name-specific arguments. There is only one, which is the signature. And this predicate actually doesn't care about the system time at all. It just verifies the signature with a parameter, the public key, and that's it. It's basically writing this in the Unicity system. It's maybe is encoded differently than the public key, but it's completely equivalent to having public key in the system. Okay, let's go to the next example. We may also implement multi-signature predicate. Multi-signature predicate has n public keys as the parameter, and the name-specific arguments, it requires n signatures. So you have to sign the same m, basically, with all the corresponding private keys. We also have a bit more complicated version of multi-signature. It's a threshold signature. We have as argument also an integer, which is between 1 and n, and it basically says how many signatures do we need. Even if we have a total n public keys, we may need just, say, half of them sign the message. So we have as arguments k pairs of signature and index, which public key it is intended to verify with, and then we just verify those signatures with the corresponding public keys. And also we have to require that those indices are all different. So otherwise we just create a single signature, put every index equal to, say the first signature, and this is not in the spirit of requiring k signatures. So we have to also verify that all these indices are different. Okay, let's go to the next example. It's from you can do another kind of atomic swaps with those predicates in Bitcoin type systems. It's called hash time lock predicate. It has as parameters 2 public keys and a hash value and a timeout. And to satisfy the predicate, you have to present an X, a hash value, and a signature, and the predicate itself is defined in a way that it's true in 2 of the occasions, either occasion A or occasion B. Occasion A is that the signature verifies with the second public key, but you then also require that X is the pre-image of this Y. So X should also be presented as an argument. And then we also require that the system time does not exceed the timeout. So the second user can satisfy the predicate before the timeout if he or she presents the pre-image of Y. And there is another occasion when the predicate is true. when the signature is given with the first public key and the timeout is exceeded. Okay, so these predicates can be combined, and we will not talk about this kind of atomic swaps today. Okay, so you may ask, how are predicates stored? Predicates are they're very much like public keys. They can be encoded as, say, octet strings. The first octet, say, is a predicate code. I don't say that we have to implement exactly like this, but predicates are just octet strings, nothing else. Okay. Say again.
It's the same mode as Bitcoin script.
Yeah, it's a locking script. Okay, so first step, how to do the same thing, the state transfer with predicates. So now we have states of tokens that are not just public key and hash pairs, but they are public key, that they are predicate and hash pairs. So this new is a predicate encoded somehow in the way we choose to encode the predicates, and we have a hash value, as in the current case. Transaction is very similar, just the new owner is again a predicate. To unlock the transaction, or to sign a transaction, we have to satisfy the predicate. So we have to provide an argument u so that this predicate is satisfied. And also, yeah, predicates may also, as you saw in the last example, they may also require something about the time. Okay. And everything else is exactly the same. We have to certify the transaction, and we have to send request to the Unicity service. Now the request contains not just public key, but in general a predicate. We do this, we get the inclusion proof, and we create certified transaction, which now consists of the unlocking script, not just signature. And if everything is done properly, we have this kind of verification identity. So the signature should verify, or the signing predicate or locking predicate should verify when the time is taken from the inclusion proof that we got in this step. So the user side takes time from inclusion proofs. And we compute the next state in a similar way. Okay, that's clear. Nothing special here. So let's talk about the Unicity service too. Now we have predicate here as well. So we have requests, and which contain predicates. Now we again compute those hashes like we did in the previous case. We check whether this place is empty. We now verify the predicate and assign this value v and the unlocking arguments, unlocking script. And we return the inclusion proof. Status queries are exactly the same. And we have a verification function as well, similar to the previous case. Here. Okay, let's talk about atomic swap now. So We have two tokens, say token A, token B, their owners I and P respectively, so that before the swap, A owns token A, P owns token B, but after swap, we want B to own token A and A to own token B. It would be very nice if we had a protocol that always guarantees this to happen. Unfortunately, we have practical restrictions. We can't guarantee this with absolute certainty. So instead, we rely on a protocol, swap protocol, and we want the following two properties to hold. If A and B follow the protocol, then swap should happen. They follow means that they indeed send the messages they are supposed to send, and the messages will be received as they are supposed to receive. But if anything happens, or A or B deviates from the protocol, either maliciously or non-maliciously, then A and B will get their tokens back, say after a timeout. And during this protocol, tokens may be in states where no party really controls them. So we can't, during the protocol, we can't always say who controls the token because we don't know additional information that opening or satisfying the predicates needs. Okay, so about the swap protocol. We have several steps here. So first is the preparation step, where the tokens are sent to preparation states. And the special states, we will go through them later. And the parties agree on a timeout. Now the parties exchange the full token ledgers. A gives her ledger to B, and B gives his ledger to A. And they check whether those tokens are indeed in preparation states. They are prepared. Now the third phase will happen, the commit phase, where the parties are supposed to transfer their tokens to swap states. Everything may happen here. So say A just quits, does not want to do that. B may quit, they both may quit, or in a optimistic case, both will do as specified. Okay, and what are those swap states? They can be defined with suitable predicates that we will describe later. And these predicates are defined in a way that if, say, token A is in the swap state, then one of those two cases happen. B will control token A if B committed token B before timeout. So if token A is in a proper commitment state, then B will control it if he committed properly. Okay, and vice versa. So if token B is in the swap state, then A will control token B if A committed token A before timeout properly. And B will control token B if A did not commit in time or did not commit at all. Okay, so a little bit of details. We have preparation states. In preparation states, the first token of A is in this state. So the ownership predicate is the preparation predicate with parameter the public key of A. And the similar about B's token. So these are special predicates, which I will describe later. Then we have swap transactions. They should contain the same hash values, as were here, and they have a data part as well. And the data part is kind of special. It contains this, for A, it contains the swap predicate with such arguments, including the timeout. And it has no mask. Mask is a constant, it's 0, and no additional information. And this is because this should be deterministic in this protocol. We'll see it later. Okay, and then if those transactions happen, then the new states will be the new hashes will be like this. So they are just as I described in one of the first slides. They're just iterated. Recall that this is in the place of x here. So we know that x is 0, should be 0. And the swap state are then as follows. Now the swap predicates, just you should see that here the B's token, the B's public key and the B's hash is in the first place and A's hash is in the second place. They're in the opposite order. Okay, and it's a crucial property of this protocol. Why it works is that all those states and messages are deterministic functions of those swap parameters. So, and why this is assumed in the Unicity infrastructure, parties only have their own information that has been sent to them. And additionally, they have access to the Unicity service. So they can't be assumed to receive any information because, as I said, parties may just quit during the protocol and do nothing, send nothing to the other party. Okay, so what is the preparation predicate? It has one parameter, the public key. Note that if the token is in the preparation state, then the previous owner still has full control over the token. He can transfer it to another state, or if he wants to follow the swap, it transfers to the special swap state. But we can't guarantee that. So, but the most important here is to mention that preparing a token does not mean you will lose control over it. You still have full control over the token. Okay, so for this predicate, it seems to be very similar to the signature verification predicate. However, to satisfy the predicate, you have to not just provide the signature, but also kind of show what you have signed. And you have to provide the data part of the transaction, you signed it, and the hash. And the predicate itself is given those arguments is verified as follows. First, the signature is verified on M. M is the standard argument. Then M, it is checked whether M is actually the message hash, the transaction hash with H and D. Then D is now examined, whether D is the proper swap transaction. Yeah. So it basically, the predicate knows whether this the next transaction in the preparation state was a proper swap transaction or not. Okay. So if it happens to be such type of transaction. The same public key here, the same hash here, some other parameters here, which we don't know yet. Then this is only possible if the current time, tau is the current time at the Unicity service, or if it's verified at the Unicity service, it's just an argument of the predicate. It's the first standard argument. And this should not exceed this timeout, which is in the predicate, which is included in D. So this is all verified by the predicate. Okay. And so if T is a swap transaction that changes this, the preparation state to a proper swap state, then this transaction cannot be certified after the timeout. So that's what this predicate guarantees. That's why we have to prepare tokens before the swap. Okay, let's go on with the swap predicate. You already know what the parameters are, so now how to satisfy the predicate. We have to provide a hash value, a inclusion proof, and the signature. And the predicate is defined as follows. So first we kind of verify the inclusion proof. We have, I will explain later. So we have a function that checks whether at this key in the repository of the Unicity service, V is stored. So if we have pi, we can verify pi and check whether this is true or not. If we have at the Unicity service side, Unicity service can just check whether V is stored at this key. Okay. So yeah, so first we check this. I mean, the predicate checks this, then it computes the preparation, the other party's preparation state, basically, and it also stores, it also assigns V prime swap. This hash, this is basically the proper swap transaction with the arguments reversed. So it basically checks whether the other party has committed properly. Yeah. Okay, and now we have already two possible ways of satisfying the predicate. So either the signature is the second party signature, if indeed the second token was committed properly. So this means that at this key, a proper value is stored. This is the only thing type of information we can verify in the Unicity infrastructure and based on the parameters we have. And the second way how to satisfy it, that the signature is verifies with the first public key, and something else was stored in, or nothing was stored. So if there's nothing, this means that nothing is equal to V prime swap, of course, and this should be later than the timeouts. So this means that the owner of the second public key can satisfy the predicate if the proper value is stored at the index that corresponds to the second party's preparation state. And the owner of the first, the token of the first public key can satisfy this predicate after the timeout if something else was stored at that key, or nothing was stored. No. So yeah, so how to evaluate this? So this is how to, so this is a specification of the predicate. And the point is that the code that implements the predicate is different at the Unicity service side and at the user side. So because we don't want to burden the Unicity service to verify inclusion proofs of the past. So it's sufficient for the Unicity service to just do a direct check, completely ignoring the spy. At user side, however, we don't have this registry available, so we have to rely on this verification function. And we can show that it doesn't matter. Everything works correctly if Unicity service and clients evaluate this predicate in different ways. Okay. So more or less, the idea is understandable. Yeah? So in the paper that is upcoming, we also provide you with the proofs that it really works under the assumptions that the hash function is collision-free and the signature scheme is existentially unforgeable. Now, yeah. So I also added a slide where all the message flow of the swap step is commit step is depicted. So what party A computes, what is sent to the Unicity service, and how the next certified transaction is formed. So we will not go through it in detail. You will have the slides, and you can examine this by yourself. Thank you for attention.